Hello, everyone. Thanks for coming to our presentation. I'm Zhongyu from UC Berkeley. I'm going to present our work on animated Cassie, which, according to the best of our knowledge, is one of the first dynamic relatable robotic characters. In movies, robot characters are full of life and are emotive, but they are virtual characters and only live in our screens. However, robots living in real world are inanimated characters, and sometimes they look awkward. Creating robots with emotional personalities will transform the usability of robots in the real world. Robots need to be relatable. As you may say, the animation is a powerful tool for behavior design, and this has been widely used in the entertainment industry. So, can we bridge the animation and the real-life robot, especially for person-sized humanoid robots, and to enable the robots to behave emotively? In this work, we try to address this problem. Here is a preview of our results. So this is Blender, a 3D creation suite. In Blender, we can draw and modify the virtual characters' motions interactively with visual effects. Later, we develop an end-to-end framework which includes dynamic organization and the real-time control to bring the virtual character to life. This is Happy Motion. The right corner shows their original animation. So here comes the set motion. So we will introduce more experiment results later. So first of all, why Cassie? Most social robots are statically stable. They are either lack of mobility, or small mobile robots, or person-sized ones with heavy bases. Their capacity to convey emotions is limited to the simplistic visual cues and can barely use body language to interact with humans. Conversely, dynamically stable robots, especially humanoid robots like Cassie, can move and convey emotions with much more agility and success. But this is much more challenging. Therefore, we developed an end-to-end pipeline to bring the animation to real Cassie. Firstly, we use the animation method to design emotive motions for the virtual characters of Cassie, but the animated motions are purely kinematics. Then, we translate the animated motion to be dynamically feasible for the robot while staying close to the animation. So this can be an optimization problem. Later, we develop a real-time standing and walking controller to enable the robot to perform the optimized motions while balancing. So here comes to the first part of our work, the animation creation. In real life, each leg on Cassie has 5 actuated rotational joints and 2 passive joints. We also define the virtual leg length and the leg angle on each leg. Moreover, we add a tablet to display designed visual eye expressions. Based on this, we create a character model of Cassie in the virtual world. The green bones maps the corresponding link on Cassie, and the joints between bones are kinematics connection. We also add target bones such as pelvis target to determine the pelvis pose, the leg pose targets to change the leg's orientation, and the foot targets to position 2 feet. In this way, the animator can just place the position of target bones, and we provide a custom solver to solve the inverse kinematics problem. During the behavior design, the animation techniques allows the animator to focus on the creation of keyframes. The poses in the frames between 2 adjacent keyframes will be interpolated automatically. In the motion paths, the yellow dots indicate the keyframes, and the continuous curves are interpolated among keyframes. Also, as we introduced before, we add eyes to provide visual cues of emotions. The eye motion can be designed jointly with the body motion. In the left figure, there are eyes for happy, angry, and sad emotions, respectively. Once the animated motion is complete, we can render it in Blender to create a professional animated movie. This is an example of a rendered tide motion. However, the animated motion is purely kinematic and is very likely to fail on a dynamic robot because it may violate certain laws of physics. This video shows the Cassie falls over when we set the real-time controller to check the animated motion in a high-fidelity simulation. Therefore, we need to optimize for a trajectory that is dynamically feasible, enforced by various constraints, while also being close to the animation. We solve this by formulating a direct collocation-based nonlinear optimization. For standing motion, one challenge we faced is that the input animated motion can be arbitrarily long. It can even be tens of seconds, which result in thousands of collocation nodes. And the direct collocation at that large time spans is computationally hard to optimize. Therefore, we proposed a following schematic. Firstly, we break the animation trajectory into sub-motions, in which contains solvable number of nodes. For each sub-motions, we formulate the optimization problem as follows. We minimize the square of L2 distance between the animated poles and the optimized ones, while enforcing the full order dynamics between adjacent nodes. We also add non-slippery constraint on the feet and other constraints to enforce the center of mass to stay inside the support region. This will result in a dynamically feasible sub-trajectory. Then, we can go to the next sub-motion and solve the same optimization problem again. Moreover, in order to connect two adjacent sub-motion, we add a position constraints to enforce the start nodes of the current sub-motion to overlap with the end node of the last one. Also, we add a velocity constraint to smooth the connection. Moreover, as you may notice, the next sub-motion starts delta nodes ahead of the end node of the last one. This will also smooth the connection. In this way, we can obtain optimized motions with arbitrary time spans. Here is a case study. The animation shows the Cassie looking for the laser point on the ground while standing. However, this animated motion causes Cassie to fall. This is because that the animated motion changes so fast. So let's see these two figures. They compare the pelvis motion in the animation and the one after optimization. The left figure shows the pelvis transitional position, XYZ, and the right figure shows the pelvis rotational position, rho PGO, denoted as Q phi, Q theta, and Q phi. The dashed line is the animated motion, while the solid line shows the optimized motion. As you can see, the pelvis yaw, the red line, changes over 50 degrees within 1 second in the animation. This is already beyond what the robots can achieve. As shown in the solid line, after optimization, the motion becomes much more smoother. Further, we can see that although there is no motion in the pelvis row in the animation, which is shown as the blue line, the optimization adds a significant movement on that degree of freedom to compensate the fast change of the motion from other degree of freedoms. The optimized motion will not cause failure, even though the motion is as aggressive as their animation one. So for optimization on walking, we chose to design a gate library that contains various gates of different gate parameters and let the robot to check the parameters from animation. So for a walking robot, a gate is defined as a periodical joint position and velocity profiles for all actuated joints. For each gate, there is a gate parameters that identify it. In our case, the gate parameter includes the pelvis sagittal velocity Vx, lateral velocity Vy, and the walking height h. The optimization is applied on a hybrid walking model. It includes constraints such as average walking velocity and walking height to match the given gate parameter, and the virtual constraint to have hybrid zero dynamics, which is impact invariant. Then we obtain a gate library containing over 1,000 gates with different gate parameters. So here is an example of gate that walks forward as 1 meter per second and is at a normal walking height. And this one, the right one, shows the low walking height and walks backwards and sideways. Once a library of a dynamical feasible motions is obtained, we need a real-time controller for Cassie to replay the input motions. For standing, the inputs are the motions of all motors from the desired motion, except 2 feet. The foot position do not check the input motion, but rather to keep the feet on the ground and to reject the perturbation. For walking, at each time step, a desired gait is obtained by interpolating the gait library with respect to the observed robot's gait parameters, which is Vx, Vy, and walking height. To maintain stable walking gait and check the reference gait parameters, a PD-based gait regulator is applied to the desired gait. The resulted motor position and the velocity are sent to joint level PD controllers to generate the motor torques. Moreover, this walking controller has a gain scheduling module wherein the PD gains are scheduled based on the reference walking height. This is achieved by interpolating a lookup parameter table with respect to the desired walking height. Such controller is one of the first that is able to significantly change the walking height for a 3D bipedal robot. For online purpose, we also develop a high-level state machine to concatenate different pre-designed motions and transition in between to form a continuous motion for the controllers to check. So here comes to our final result. We can design emotive behavior for the virtual characters of Cassie. Then we apply the entire pipeline we just introduced and make Cassie to perform the design emotive and the expressive motions with personalities. We call it dynamic relatable robotic character. So this is happy motion and sad motion. And tired motion, which is a sleepy motion. And here comes to the chasing laser point on the ground. Moreover, we are the first to achieve variable walking height control on a bipedal robot Cassie. Okay, these are all the materials. Thank you. Questions and suggestions are welcome.